In the past few units, we've been talking about matter, right? You matter, I matter, everyone matters, everyone's made of matter. In this video, we are going to start transitioning, and in this unit, we are going to start transitioning into light and energy. And to do that, we're going to have to focus on electrons. So this video is just a brief follow-up to the electron, energy, and light puzzle, which you have already completed / are in the progress of completing. So we are just going to jump right in. Matter is made of atoms, meaning that it's made up of protons, neutrons, and electrons. So then what is light? Light's everything else. So if it's made up of protons, neutrons, and electrons, it's matter, it's atoms, everything else is considered light. Light is also called energy or electromagnetic radiation. Those are all synonymous with each other. Basically, if you can touch it, it's matter. Otherwise, it's energy or light. So let's get into a couple of definitions with light. We have, here are my pictures. Wavelength is the distance between 2 points on a wave. Light travels as a wave, as shown in these red lines here. The wavelength is the distance between 2 points, crest to crest, or trough to trough. So in this picture here, we have crest to crest. All right, the crests are the top, and then in this picture over here, if we went trough to trough, that would also be one wavelength. Okay, the amplitude is the height of the wave. So the distance from the origin, or this middle black line here, to the crest, or the middle line to the trough. So the amplitude is not the whole distance, it's just from the middle black line to either the crest or the origin there to the trough. There are 3 things that we can measure about light. In addition to wavelength and amplitude, we can also measure frequency. Frequency is the number of waves that pass through a particular point in 1 second. So if we go back to this image on the last slide, this wave A here has a lower frequency than wave B. If there was some arbitrary point right here, right, wave B would have more waves pass through that point in any given second than wave A. So wave B had a higher frequency than wave A. And this is measured in waves per second, or sometimes the waves is left off and it's just per seconds, or seconds to the negative first. We can also measure the wavelength, as I just said. These are Greek letters here, sorry, I should mention that. This is the Greek letter nu, it's like a weird V, and this is the Greek letter lambda. Lambda, wavelength, is measured in meters. It's a distance unit. But you will often see meters or nanometers is what we will use a lot. You can also measure the speed of the wave. All light waves travel at the same speed, and that's 3.00 times 10 to the 8th meters per second. This is, I'm sure you've heard, the speed of light, and that's in meters per second. So that's pretty fast. You guys know how long a meter is. 3.00 times 10 to the 8th meters per second is pretty dang quick. All right, so we can measure all 3 of these things about light waves. We can also measure amplitude, as I mentioned on the previous slide, but that doesn't really tell us a lot about any energy necessarily. These are the 3 things that you'll see most often. So let's talk about speed. Which of these waves here is faster? Well, the red wave, wave A, has a longer wavelength, but it has a lower frequency. Wave B has a shorter wavelength, but it has a much higher frequency. These are both light waves, which means they both travel at that speed of light. The symbol for the speed of light is c. One light wave can travel around the Earth 10 times in 1 second. So like I said, that's pretty freaking fast. When we talk about light, you often will hear us talk about the electromagnetic spectrum. So this is all of the light waves, all of the distinctions in light that we have. We've got gamma rays, which we've been talking about, gamma radiation, right, folks? So those are all the way down here. They have very short frequencies, so times 10 to the negative 12th frequency. So they're like wee, like really, I can't even draw them as close together as they would need to be. All right, really, really short wavelength, which means they have a very high frequency. Then there's X-rays, ultraviolet. We have visible light down here, which is, actually right in here. This is the portion that we can see. Then there's also infrared, microwaves, and radio waves. So along the top here, what these images are, that tells you about the wavelength in meters. So the wavelength of a radio wave is pretty large. It's like the length of a human. Microwave, we're getting more like the length of a fingernail. Pinhead, those are pretty short, right? If we get down to gamma rays, they are smaller than the atom. That's how tiny those wavelengths are. So just a big overview here of the electromagnetic spectrum. Like I said, we've already talked a little bit about gamma and X-rays. We're going to focus this unit mostly on visible, sometimes UV, and infrared light. But like I said, we're focusing on visible light. So that's a great question. What is color? Well, color is based on the wavelength and frequency of light waves, and therefore the energy of those waves. Some light that we see has all of the colors together, right? If we look at white light, so from a flashlight or from the fluorescent lights in our classroom, it looks like one light. But you guys have seen those prisms, right? Where if you hold them up just right, they reflect that whole rainbow. So color depends on the energy of those waves. So the color that we see is literally light being emitted from whatever the object is that is emitting that color. Visible light ranges from 400 nanometers to 800 nanometers. So this is the 400 nanometer range. This is the more like 700 nanometer range down here at red. My favorite color is 415 nanometers. What's your favorite color? I might ask you that on a Google Classroom question, actually. So think about what your favorite color is, knowing what the wavelengths of visible light is. Real question though. What is light made of? This is a big issue. It's not made of matter, right? Matter is protons, neutrons, and electrons. Well, through a series of highly complicated experiments, Einstein said, well, light must be made of matter because light can move matter. So light must also be made of matter. This is called the photoelectric effect, and we're not going to get into it too much right now, but you should know. Right? Einstein said that light must be made of matter, but it doesn't have mass. So he called those he called those light particles photons. He said these photons have no mass, but they carry energy. They're made of matter, sort of. So it gets kind of complicated, right? These photons have no mass, but they carry energy. More photons, more energy, which means you can move more matter with more energy. All right, so in this picture down here on the left, we have a larger wavelength, okay, very long wavelength, and it carries fewer photons. Whereas over here, we have a very high or very short wavelength, very high frequency, and we have lots of photons. That means that this is more energy, right? So higher frequency means higher energy. Lower frequency means lower energy. So let's get into that a little bit deeper. We know that substances can absorb energy, and if they can absorb energy, then they can also release energy. That energy can be released in all forms. So thinking about the electromagnetic spectrum, we see a lot of light that is released in the visible spectrum. But sometimes infrared light is released, UV light, gamma, right? Gamma rays can be released as energy. A lot of things happen. And that's all caused by atoms releasing energy. So Bohr, our good pal Bohr, he took those ideas from Einstein about photons and about atoms releasing energy, and he started thinking about that in the context of atomic structure. So let's go back in time to before we knew who Bohr was and what the planetary model was. Bohr took hydrogen and he studied it in depth. Right? He picked hydrogen to study because hydrogen is the most simple element. It only has one proton, so it only has one electron. So seemingly it would be the simplest atom to study. Now Bohr knew already, because of Rutherford, that the protons and the neutrons were stuck in the nucleus. So that's why he said, okay, well maybe let's focus on the electrons. Maybe it's their job to release this energy. He knew that they could move around. He figured that if he could excite the one electron that's in hydrogen, he would see some type of energy released, potentially in the form of light, right? That's when he saw the first atomic emission spectra of hydrogen. He excited that electron, that one pesky electron in hydrogen, and he saw that it emitted a very soft purple, almost lavender light. And when that light was split up with a prism, just like when we have white light that goes through a prism and it breaks into the whole rainbow, right? Roy G. Biv. When he held up a prism to this soft purple light, he saw that it actually split into 4 different wavelengths of light. So here's a picture of what that looked like here. We've got the soft purple glow from hydrogen. We've got it being split up in a prism. All right, this actually shows 5. A lot of times you see that 2 of these join together. All right, but we've got all these different wavelengths of light over here, which was a little bit peculiar because hydrogen only has 1 electron. But as you learned in the POGL, there are lots of hydrogen atoms in that gas discharge tube. So lots of electrons, even though they're all in individual hydrogen atoms, means that we can still have a lot of energy transitions. So Bohr's thinking about, well, all those electrons can move, but in order for us to get those different wavelengths of light, those electrons must be moving to different locations within the atom. And that's where his idea for energy levels came from. He said, okay, there's multiple lines on this line spectra, which means that there must be different energy levels within the atom, and that's why hydrogen can emit more than 1 wavelength of light. Each of those 4 lines represented 1 electron, or in the gas discharge tube, multiple atoms of hydrogen, moving to different locations. He called those energy levels because each level had a specific energy associated with it, right? Each line in the line spectra was a different color. Each color represented a different energy of light. That's why they're called energy levels. And this supported Planck's and Einstein's quantum theory of the electrons being outside of the nucleus and having mass and energy. So diving a little bit further into the atomic emission spectra, right, Bohr, and working within Einstein's theory, is saying that an electron can absorb a photon of light. So remember that a photon of light does not have mass, but it carries energy. So 1 electron can absorb energy, which will cause it to jump up to a higher energy level, symbolized with an N. N stands for energy level. So if we think of our Bohr model here, we've got circle, that's our nucleus. We've got energy levels around it. Bohr is saying that if we have an electron, and it's down here in the first energy level, if it absorbs energy, right, so drawing an arrow jumping up, it's absorbing energy. It can jump up to a higher energy level. So this first energy level will be n equals 1, n equals 2, n equals 3. Let's label that. N equals 1, n equals 2, n equals 3. When the electron that got excited, it absorbed energy to get up here, but it can't just contain that energy forever. So eventually that electron is going to release energy and fall back down. And when it does, it releases energy in the form of light. So now we have light, yay, being released from that electron transition, and you saw that in the POGL as well. And that's what creates the line spectra. Since each element contains a unique number of electrons, right, we're not talking about hydrogen anymore, we can get unique line spectra for each atom. So each element can be identified by its unique line spectra. It's like a fingerprint in humans. So some terms that you need to know. Here in my little Bohr model, it's much better than my hastily drawn one. We have the nucleus right here. Right? We have the first energy level, second energy level, third energy level, fourth energy level. And let's say that we had an electron right here. Well, let's say that electron absorbs energy, jumps up to the fourth energy level. When it falls back down, depending on where it falls to or where it jumped up to, it's going to release that light. So we have some terms that you need to know. That low energy level, so in this case the first energy level, is called the ground state. So that's all electrons in the lowest energy level possible. When that electron absorbs energy, it jumps up to an excited state. Now it's all excited, it's jumping all across the room, woo, woo, woo! It's got energy, it's excited, it's had its morning caffeine. But that excited state is unstable, just like a caffeine rush, and that electron will eventually fall back down to the ground state, and that's when I need my afternoon nap, right in the middle of 8th hour. It's okay, I get through it. So that excited state unstable, the electron falls back down, and that's when it emits light. And that's when we see these really beautiful atomic emission spectra. This is what the sun looks like. So it's emitting all of this light with the exception of just a few wavelengths there. Then this is hydrogen. Here's the 4. Right, like I said earlier, it really should be 4 wavelengths of light for hydrogen. Helium's got more. Mercury, uranium has so many. Oh my gosh. And we are going to get to see some of these atomic emission spectra in class. Or I have a book of every element's unique atomic emission spectra that I will happily show you. It's my favorite book ever. I got it for Christmas. It's awesome. More specifically, here are the breakdown of the energy level transitions that you talked about in the POGL. All right, so we see all of these different colors. They're caused by electrons jumping up and falling down to different wavelengths of light. So when the electrons get excited up to the 7th energy level, if they fall down to the 2nd energy level, they'll emit blue light. It doesn't always happen like that, right? Sometimes they'll emit UV light, we won't be able to see it. Sometimes they'll emit infrared light, and we won't be able to see it. But this is your sort of series here. This is for the hydrogen atom. It's one electron. If it can make any of these jumps, this is the type of energy that will be emitted. So like I said, this was a very quick run through electrons and light and energy and a little bit of matter, question mark, photons, cool. We're going to keep exploring all of this through this unit. So make sure that you go back to that POGL, make sure you really understand all the pieces there, and we will see you in the lab to do some cool experiments.